测试中，有没有问题？现在可以了吗？有没有听到？现在有没有听到？有没有听到？可以了吗？可以了吗？听得到吗？听得到吗？喂喂，就是这里，这里，哎。喂喂，
现在还是没声音，
没有声音，没声音，
到时候要等我一下。
好，没关系，
我没事。
哎，对，可以，对了，有声音了，有了，好，
又没有，
有，
等下为什么奇怪？
有没有？有了，好，听得清楚啊？Can you hear? Can you hear clearly?
有
Okay, can you hear clearly?
又没。
有。
等下为什么奇怪
？Okay. 这样子声音好。哎，有，可以，还是没有？啊？没有，还是没有？
还没有。
哎，可以吗？哎，听一下。有。OK。可以。听一下，还有没有吗？可以吗？
断断续续的。
喂，断续续的，他这个南区应该是，可以吗？Hello。
现在
OK 了，现在 OK 了。OK 了。
那应该先可以继续上。
好，我们可以继续上课哈。好，那我们这个班列什么？这个班列什么？这个。
这个吗？
班列的哈，这个班的哈。OK 好。All right. Now this is the second page for the slides, and I showed you this before already. Let us just start with a very simple mass spring despot system. Define the equation of motions, which is the equation of motion, which is this. The m w dot plus zeta dot plus kw equal to f, and also define the natural frequencies is omega n equal to square root of k over m, and the the period is tau equal to 2 pi divided by omega n. Damping factor or damping ratio is zeta n equal to zeta divided by 2m omega n. And then we will be able to write equation of motion in terms of w double dot plus 2 zeta n omega n w plus omega n square w equal to f divided by n. You gotta be focused on only two parameters. One omega n and another zeta n. For these equations, the m, we move the m to the right hand side. That's divided f divided by m. That's our new force. All right. Then I think we already talked about this. That's equation of motions, and I will show you the eigenvalues and the eigenvectors later. How the eigenvalue related to this equation of motions. So most of the time we write equation of motion in terms of this simple w double dot plus 2 zeta n omega n plus omega n square w equal to f divided by n. Now assume we say there's no f. That means we are solving only the homogeneous solutions at this moment. Because the eigenvalue and eigenvectors of a system, those are related to the homogeneous solution of the system. So we know that if we want to solve this equation of motion, then we have to solve this called characteristics polynomial. So give us two roots, lambda. And these two roots, lambda 1 and lambda 2, they are related. So lambda 1 is omega n, and then parenthesis minus zeta n plus square root zeta n square minus 1. Lambda 2 is minus zeta n and minus square root zeta n square minus 1. So each equation of motion like this, the spring desktop and mass, has two roots. Any mechanical system, the simplest mechanical system has two roots. They come with a pair, all right? And our general solutions, the general solution is on the bottom here, Wt equal to A1 exponential lambda 1t plus A2 exponential lambda 2t. Or you can, then lambda 1 and lambda 2 are just the roots of that polynomial. As a matter of fact, this lambda 1 and lambda 2 are also the eigenvalues that I'm going to show you for that. So, the third page, if you look at the third page here, all right, so I'm going to show you how this equation of motion, the second order equation of motion, related to the first order equation of motion. So the second order equation of motion, then you can write in the first order equation of motion, and that's the way you do. We put the w dot and w double dot on the left hand side, and then on the right hand side, then I have zeta 1 minus omega n square minus 2 zeta n and omega n, and then multiplied by the w and w dot on this right hand side here, and then plus zeta 1 f divided by n. So f divided by n, that's another forcing here. Okay, the same thing. If we assume that we have the state vector to be, there's a sine 1 and sine 2 here. So look at this sine 1 and sine 2. We should call phi 1. Now phi 1 and phi 2, and I'll call exponential lambda t. Then you sub this solution into the first order equations, then you will be able to find out that this first order equation of motion, then phi 1 phi 2 times lambda exponential lambda t minus then parenthesis 0, 1 minus omega n squared minus 2 zeta n wn, and then phi1, phi2, e lambda n t equal to 0, 1 and fn. Now, of course, later on we assume that we don't have f here, but this is the whole equation of motion in terms of first order form. So our mechanical system always in the second order form like this. So we always have w double dot. But in the control theory, we always convert it to the first order equation of motion like this. And so you will be able to see that the matrix, so we have a matrix here. Now after that, we sub our solutions. There's a phi1 and phi2. And I will explain to you what this phi1 and phi2 mean. As a matter of fact, that's the eigenvectors. Later on, I'll show you how that worked out. So at the bottom line of this slide, if you look at that, then I put all lambda together with the state matrix. That's 0, 1 minus omega n squared minus 2 zeta n wn. And if you look at this, then we'll be able to see that lambda minus 1 and omega n lambda plus 2 zeta n omega n, the 2 by 2 matrix time phi1, phi2, and the exponential lambda t equal to then 0, 1 and fn. Of course, now in the next page you will be able to see that, assume that f equal to 0, 0, and again this is solving the homogeneous solution of the equation of motions. Now if we assume that we don't worry about f here at this moment.
所以说要讲这个，刚刚没有切过去。
哦，没有切过去。Okay, all right, sorry. So if you look at this, this equation here, then we'll be able to see that the left-hand side equations, lambda minus 1 omega squared, lambda plus 2 zeta n omega n, then phi1, phi2, e number 2 equal to 0, 0. So say we try to solve the we call the homogeneous solution of the equation of motions. And if that's the case, if this is 0, 0 and e lambda t, unless t going to infinity, lambda is negative, otherwise e lambda t will be 0. That means this matrix times phi1, phi2 equal to 0, 0. Okay, now the eigenvalue of this matrix, that's lambda, lambda. If you look at this means the determinant of this matrix equal to 0. That means lambda times lambda plus 2 zeta n omega n plus omega n squared equal to 0. And then we got this equation of motion, this equation called lambda squared plus 2 zeta n omega n lambda plus omega n squared equal to 0. That's exactly the same as the root equations called characteristics polynomial. So the eigenvalue of this matrix, of that matrix, the state matrix, the eigenvalue of, let me go back here, let's just go back here. So the eigenvalue of this first order equation of motion, that's eigenvalue of 0, 1 minus omega n squared minus 2 zeta n omega n. The eigenvalue of that, that is this. That must satisfy these polynomial equations. That means lambda squared plus 2 zeta n omega n lambda plus omega n squared equal to 0. And so our eigenvalue will be lambda 1 equal to this omega n parenthesis minus zeta n plus square root zeta n squared minus 1. And number 2 is the same thing, there's omega n minus zeta n minus square root zeta n squared minus 1. So we know that this eigenvalue are the roots of the characteristics polynomial. Okay, that's eigenvalue. How about eigenvectors? The eigenvectors means this phi1, phi2. The phi1, phi2, that if we solve, we assume we know the lambda 1 and lambda 2 are giving, then lambda minus phi1 minus phi2 equal to 0. Omega n squared phi1 plus parenthesis lambda plus 2 zeta n omega n parenthesis phi2 equals 0. So we have two equations. Then we have two unknown. One is phi1 and phi2. However, now if you look at the second one here, these two equations are not independent. So that means we'll show you in the next page, the proof in the next page. So we can write our eigenvector to be phi1, phi2 equal to 1 lambda phi1. Phi1 can be arbitrary. Any arbitrary value will be that eigenvectors. So we have eigenvector 1 lambda phi1. So each lambda, so lambda 1 has its own eigenvectors, and lambda 2 also has an eigenvectors. So we have, this is our eigenvector now. Now from here, we can conclude that any eigenvector, their amplitude is not unique. So phi1, it can be 1, it can be 2, it can be 3, it can be 2, it can be 10. Any values still is eigenvector. So 1 lambda times a constant, and that constant can be any value, because that constant does not change the directions of the eigenvector. They change the amplitude of the eigenvectors. All right. Now the next page will show you. All right. The next page will show you that the eigenvector definitions and how that eigenvectors how we compute the eigenvectors. For example, we in the last page we say phi1 phi2 equal to 1 lambda phi1. That's my eigenvectors. So let us prove that. Okay, then assume phi1 equal to 1. Say just phi1 equal to 1. All right. The phi1 equal to 1, then zeta 1 minus omega n squared minus 2 zeta n omega n times 1 lambda. That will be equal to parenthesis lambda minus omega n squared minus 2 zeta n omega n lambda equal to lambda and 1 lambda. So a matrix times a vector equal to an eigenvalue times its eigenvectors. That's the eigenvector definitions. All right. So from here, then we will know that we have two eigenvalues. That's lambda 1 and lambda 2. We have two eigenvectors. It's 1 lambda 1 and 1 lambda 2. That's our two eigenvectors. Okay. So now let me switch this back, and then I can write okay. Wait a second. Okay. All right. Let me just write a little bit here, so you will be able to understand a little bit. The eigenvalue, eigenvalue and eigenvectors. Alright? Is that better? Okay. Alright. Can you see it? No? Alright. Eigenvectors for a matrix A, C, for example, AC multiply phi equal to lambda phi, then that's a matrix. And then this is the, we call eigenvector. Alright, this is eigenvectors. And this is what we call eigenvalues. Alright, so that's the definition of eigenvector and eigenvalue. Now, if you eigenvector by any constant here, it doesn't change, right? So that means AC. Wait a second. Let me just try to erase this guy. Yeah. All right. So if this is 2 by 2 matrix, then the phi will be 2 by 1. All right. And this is the phi will be 2 by 1. And then lambda, that's a scalar. It's always a scalar. All right. So if this is 3 by 3, then this is 3 by 1. And this is still scalar. So that's the definition of eigenvalue and eigenvectors. And normally, AC, in a real system, AC is real. But lambda and phi are complex. That's normal. That's in general. If eigenvalue is a complex, then is eigenvector also a complex? Okay. Now, in this, you understand now? You have any questions? Have any questions? No? That's the definition of eigenvalue and eigenvectors. All right. So in our system there, let me just erase this. In our system, eigenvalue, we have eigenvalue 1. That's our eigenvalue 1. Then our phi 1 equal to 1 lambda 1. That's we have one eigenvalue and one eigenvector. And then number 2, then phi 2 equal to 1 number 2. Okay. That's just our system. The one I just showed you. So for a mechanic system, for any system, like a mechanic system we have, the second order system, we always come with a pair, number 1 and number 2. And so we come up with a pair of eigenvectors, that's number 1 and number 2. It happened to be just only like that, but it's not necessary always like this. However, we can normalize it. What we can normalize, call phi 1 a tilde. We can normalize this vector to become 1 plus lambda 1 square, then the square root of this, then times 1 lambda 1. normally, we normalize eigenvector become like this. That's our eigenvectors. That means the length of the eigenvector equal to 1. And the same thing, phi 2, we normalize it, so that means square root 1 over 1 plus lambda 2 square, then 1 lambda 1 and lambda 2. One second, is that normalized? Yeah. So the length of this equal to 1. Is that true? The length of a vector is the element square plus another element square and square root of that, right? That's the length. So we call this is normal eigenvectors, normalized eigenvectors. So that's we call normalized eigenvector. So when you use MATLAB or use a Scilab to solve eigenvectors, they always give you called normalized eigenvector. That means their length equal to 1. Any questions?
What's the difference between normalized eigenvector and
They don't have any. There's no effect anymore. Anyway, AC times normalized one still equal to lambda 1 normalized one. Because doesn't matter if you multiply by any constant value here, any constant value there, it doesn't change these equations. Agree? You can, this eigenvalue doesn't change, but eigenvectors just doesn't change. This is the same thing. AC phi 1 equal to lambda 1 phi 1. Agree? It doesn't change. So this is why I say the eigenvector, the length of eigenvector is not unique. The length is not unique. So you can write any eigenvectors times a constant that equal to lambda 1 times another constant. If both sides times a constant, it doesn't change the equations.
so when we have to use normalized
It doesn't have to be. You can use any length of eigenvector you want. It doesn't mean when, but in general, when you use a MATLAB, MATLAB has EIG to solve eigenvalue problem. If you use those existing software, most of the software will give you the normalized eigenvector. They automatically give you normalized eigenvectors. And also in engineering, when we try to look at the eigenvectors, we also try to normalize it. Because the length equal to 1 is easier for us to compare. For two eigenvectors, and both of them all lengths equal to 1, it's easier to compare them. So in general, we prefer to use normalized eigenvectors. I say prefer, doesn't mean it's necessary. Okay? So, that's is the eigenvectors. Now, how this eigenvector related to your homogeneous solutions? That's what I'm going to tell you. How is that? All right. Then, okay. Change back to this one here. All right, and so if you understand about the eigenvalue and eigenvectors from a matrix and from the definitions, so this is the definition of eigenvalue and eigenvectors. Here I prove to you that one number here, and you can prove yourself. As a matter of fact, if this minus omega n square minus 2 zeta n omega n lambda, this minus, that means equal to the lambda square, right? If you look at this is why I have an error here. The error here means these two terms, in matter of fact, is equal to lambda square, right? That means lambda square, if you look at this, these two terms equal to lambda times lambda square. Agree? That's how I prove it. Okay, now the next page show you the solution of your we call transient response. That means the transient response means the response with no force. That means your homogeneous equations. So you look at this, the lambda W and W dot equal to A1, that's a constant, times your eigenvectors of lambda 1 times exponential lambda 1 t. Plus A2, that's another constant, times your eigenvectors times your eigenvalue, exponential of your eigenvalue. So that means A1, 1 lambda 1, E lambda 1t plus A2, 1 lambda 2, E lambda 2t. Alright? Now, A1 and A2 are determined by your initial condition. So here I give you 3 different initial conditions. 3 different initial conditions. If initial condition both W and W dot equal to 0, then your A1 equal to 0 and A2 equal to 0. That means you have no transient response. So your system stays still if you have no initial condition, your system will stay still, right? Of course, that's the truth. Your initial condition, like the second one, is your displacement equal to 0, your velocity equal to 1. Then from here, A1, 1 lambda 1 plus A2, 1 lambda 2 equal to 0, 1. Then you solve these two equations. Then your A1 equal to minus 1 divided by lambda 1 minus lambda 2. A2 equal to 1 divided by parentheses lambda 2 minus lambda 1. That's the A1 and A2. That means you're solving your homogeneous solutions of your equation of motions. You solve your displacement and velocity simultaneously. Think about that. So this is how eigenvector and eigenvalue solving your transient response means solving your homogeneous solutions. And the same thing, if you say, okay, W equal to 1, you have initial displacement, but you don't have initial velocities. Then again, from this equation, you solve A1 and A2, like that. So A1 plus A2 equal to 1, and A1 lambda 1 plus A2 lambda 2 equal to 0. That's second equations. From these two equations, then you solve A1 and A2. So for any matrix, if you know their eigenvectors, you know their eigenvalues, you will be able to solve your transient response. This is what we call transient response of the state equations. So for any given pair of eigenvalue, one may compute their corresponding natural frequencies and damping ratio. That's my conclusions. That's exactly the same as you solving you solve from your second order equations. So you can solve second order equations, or you can solve this first order equation. You get the same solutions. So this is why I made up this set of slides to explain to you. Now, that's the same thing as I show you in my class. The same slides, and solve the A1 and A2 in different way. This A1 and A2, we solve it from the second order equations. This lambda 1 and lambda 2, we solve it from second order equations. And they are exactly the same. So, doesn't matter if lambda 1, lambda 2 solving for second order equation or first order equations, they are the eigenvalue of your system. Okay? And then here, in the notes, I say, okay, I have an initial displacement. I don't have initial velocities. Then A1 and A2 solving exact the same as what we got. Agree? Any question about this eigenvalue and eigenvectors now? They do represent some of the physical meaning. And so eigenvalue, you can just look at the eigenvalue as your roots of your second order polynomial. Same thing. So in your homework, like that, let us look at this again, because this is also important. If your lambda 1 is complex, then lambda 1 and lambda 2 must be complex and conjugate. And your eigenvector the same thing. And this is the same page in my note for responses. And here, so general state equation here. The general state equation here. Wait a second. Let me go back here to show you. Okay. I think I have. Let us go back page here to. Wait a second. Okay. All right, and lambda 1. Okay. Wait a second here. And then where's my okay. All right, that's all right. I will find it later. All right. So the general equations for any state equation like x star equal to xc acx plus bcu, and then we can also solve the same way, x equal to phi e lambda t, and then the eigenvalue problem will be phi lambda e lambda t equal to ac phi e lambda t, then lambda I, the n by n matrix. The example I give is just on 2 by 2. Minus AC, if AC is n by n matrix, then this is the eigenvector we can have. So AC times a capital phi equal to capital phi lambda, and then I have phi 1, phi 2 to phi n. I have n eigenvectors for this here. And equal to n eigenvectors times n eigenvalues. And these n eigenvalues are the diagonal. Okay, now to solve this x, then x equal to x1, x2, xn equal to phi 1, phi 2, phi n times e lambda t and e lambda 2t and e lambda nt times A1, A2, AN. I have n constants. I have to solve it if I know the initial conditions. Right? I just generalize the two-dimensional state equations become n-dimensional state equations. That's all. At the end, if you look at this, if you look at this one here, x0 equal to this phi A, because when t equals 0, this means E lambda t equal to 1. When t equals 0, this E lambda equal t equal to 1. So that A become my eigenvectors inverse times of x0. So my solution of x will be equal to cap phi times E cap lambda t, then phi inverse times x0. And that equal to E ACT x0. So that show you, this equation show you the eigenvectors and eigenvalues are related to your initial conditions. That's how you do it. Now, if you look carefully here, there's a cap phi exponential lambda t, then cap phi inverse that I claim that's equal to EACT. Do you agree? You know why? You know, right? I explain to you later. Let us look at the last page first. Here. So each pair of eigenvalues, lambda 1 will be equal to omega n. Each pair, I say each pair eigenvalue. You have an n eigenvalue. This n eigenvalue, you can pair it. Alright? Each pair eigenvalue, particularly those complex and conjugate. The complex eigenvalue, and then you have complex conjugate eigenvalue. So lambda 1 and lambda 2, then you can solve your omega n and zeta n if you know lambda 1 and lambda 2. Agree? Right? So giving lambda 1 and lambda 2 a pair, then you should be able to solve your omega n and zeta n. So if one eigenvalue is a complex, then you look at all eigenvalue, they must have another eigenvalue that's also complex. They are paired together. The complex conjugate. The same thing for eigenvectors. So the bottom line here, I show you what? How you solve the zeta n and omega n, right? Agree? So if I ignore eigenvalue, a pair eigenvalue, lambda 1, lambda 2, you should be able to also solve your omega n and your zeta n. So you should be able to solve, to find your natural frequencies and also your damping ratio. And they must be real value. Because if lambda 1 and lambda 2, both of them are real, and they are real. But if they are not, they are complex and conjugate. So complex value times its conjugate must be real, right? And add together also real. Multiple together real, add together real. So they are all real. So we don't have any, do you have any question about this page? No? Okay, now let's go back to last page. Let me explain to you that how that this cap phi multiplied E lambda t phi transpose x0. Do you agree that I can write my x here equal to 3 lambda t e cap lambda t times a. A is cap phi inverse x0, right? Any questions?
If it is not transient solution, it's particular solution. It's the same way to solve it.
Yeah, if you look at my note for that state space equations, you still have to know your transient eigenvalue first before you can solve particular solutions. Like when you solve the differential equations, you solve the homogeneous solution first, then you solve the particular solution. Agree? Yeah. So that's the same thing. And before you solve particular solution, you have to know your homogeneous solution first. Right? That's a calculus. Yeah. Okay. Then let me explain to you for this one here, because this is important since we need to understand. All right. Let me erase this guy here. This is very interesting. We most understand the eigenvalue and eigenvectors of a system before I introduce a control method called Paul-Prism technique. So if you have any question about eigenvalue, eigenvectors, you need to ask for it. All right. In this, we know that the x equal to cap phi e lambda t a, right? We have no question about that. And however, we know a, we can solve it, is 3 inverse, then that's x0, right? So x become cap phi e lambda t, then 3 inverse x0, right? Agree? No problem, right? And we know AC equal to there. AC cap phi here equal to that cap phi lambda, right? Okay, so that's no problem. Then if we look at carefully, then AC equal to 3 lambda 3 inverse, right? That's no problem too. Agree? So now we have these two equations. We have these equations. AC equal to phi cap phi cap lambda cap phi inverse. Agree? Now, what I have to prove to you is, now if I have the EACT, then that equal to phi eta t, right? Now you want me to prove this. Agree? I take exponential of this times t equal to phi, then exponential lambda t phi minus 1. inverse. Okay? You want me to prove this, right? Well, this one, now we need to multiply x0 and forget about x0. Because I haven't write that x0, right? E, A, C, T, x0. Right? That's because that's x0 there. Agree? And this is my x, t. Now, this I already proved to you there. Right? Now, I already proved to you there. Agree? Now, I have to prove now. I have to prove this, right? Now, we know that x dot equal to AC x. If this is scalar, we know that xt equal to e to AC t x0. Agree? If that's a scalar. If this is scalar. Is that right? Agree? Differential equations. If this is only a scalar, not a matrix, a scalar, you write this way. And if this is the matrix, equal, these two is still equal. Matter of fact, this very interestingly that like this eigenvalue such that you can, this eigenvectors doesn't change. You take exponential of eigenvalue only and then multiply eigenvalue inverse. Then x0 that equal to EACT. So one way to solve EACT is solve the eigenvalue eigenvectors of AC, and then this is your solution. Because this is matrix. Don't forget this is matrix. Now, we just erase this. Now, AC, lambda C equal to a, this is lambda 1, lambda 2, this is the call what diagonal matrix. Right? Then e to the ACT for a diagonal matrix, not AC. Sorry, this is lambda. Lambda. CT. That equal to, in matter of fact, it's E lambda 1 T 0, 0, 0, E lambda 2 T 0, 0, 0, E lambda n T. That takes a diagonal matrix, exponential of the diagonal matrix means that you take the exponential of all the diagonal element. Okay? But if this is not diagonal, you cannot do that. Okay? So only the diagonal matrix you can write like this. If that is not diagonal matrix, you cannot write like this. questions? Now, this set of slides, I made it to just to be to help you to look at the homework, number 6 or number 5. I ask you the damping ratio, frequencies, natural frequencies. Did you remember that problems? And after that, I receive many questions from students. So I decided to get another set of slides, make the eigenvalues and eigenvectors relationship with the natural frequencies and damping ratio. All right. So, doesn't matter how many eigenvalues you have, or how many eigenvectors you have, as long as you know the pair, each pair of eigenvalues, you should be able to solve the natural frequencies and the damping ratio. Any problem now? No? Okay, now if no, I will move on to the lectures. Let me close this file, and I need to open another file, the venture space.
我已经去买开好，
Okay.
我知道。好，真的好。
Okay. Come on, there. Yeah. Okay. Good. And I need to close this guy. And I need to do this. Venture space. All right. Now we talk about null space, Collins space, null space. Here I'm going to hopefully complete this set quickly. We talked about the Collins space last week, and the basis vectors for the Collins space is very easy. You can just use these two columns. Those are the basis vectors too, 1, 0, 2, and 0, 1, 0. And then you can create the column space. So I have a V1 and V2. That's the column space. And for null space, wait a second. Right. Oh, why? Okay. Then that's my column space. That's my column space. That means just a plane, right? Just three coordinate, but we have this the 1, 0, 2 and 0, 1, 0 as your basis vectors, and create a column space, and not use column space. And C1 and C2 are the arbitrary value. So you give them all possible values, real values, then it creates a space, which is a plane, just nothing but a plane, right? In the three-dimensional space, it's nothing but just a plane. That's why we call column space. Oops, I don't know why I keep giving back this guy. Wait a second. Okay. All right, and then column null space. Column null space is the orthogonal to that. So orthogonal to that. That means a space, a vector, or a space orthogonal to your column space. Now, what is the space that orthogonal to your column space? that will be your column null space. For this case, for this example, now your column null space nothing but just a vector. Alright, so that means the 102, 102 or 010, any column vectors x1, x2, x3 that are orthogonal to these two vectors. And that means the x1 plus 2x2 and x2 equal to 0, 0. And solve these equations, then we'll be able to get a basis vector called 1, 0, minus 0.5. So 1, 0, minus 0.5 will become your basis vectors for your null space, column null space. And that's the column null space, the basis vectors. If you look at this, the basis vectors, that is the vector that create your space. And for these examples, the null space has only one basis vectors, only one. It can be 2, it can be 3, but this is only one. And I'll show you later some other examples soon. And for that, if you look carefully, this is my column null space. And then let us look at the row space of vectors, of a matrix. The row space of a matrix means its row as a basis vectors. So that you have a W1, that's W1 is A11, A12 to A1n, W2 is A21, A22 to A2n, W2 to Wn is AN1, AN2, AM1, AM2, AMN, that's my Wm. So I have a total of m vectors, but those are row vectors. So these row vectors, like a C1, W1 plus C2, W2 plus Cm, Wm. So we have a total of m constants, the arbitrary constants. Then these m arbitrary constants will create a space called row space. So that's in the row space. Now let's look at this example, the same example. So we have W1 equal to 1, 0, W2 equal to 0, 1, W3 is 2, 0. Now I have 3 basis vectors for row, but again, these 3 vectors are not independent. If you look carefully for those 2 vectors, the W1 and W3, they are not independent. Agree? W3 equal to 2 W1. So these 3 vectors, row vectors, they are not independent, but doesn't matter. We can still use those 3 vectors to create a space. And that's what we call the row space. And here, C1 and C2 and C3 are arbitrary for this case. And so then you create, we call row space. Then another, we call row space. The row space means that any row that will be orthogonal to your 2 rows. So do we have any row that are orthogonal to this 3 rows? That's 3 rows. So X A transpose. Now x1 times x2. Now if we solve this, we find out that x1 equals 0 and x2 equals 0. That means we have no row null space. In this case, there's no row null space. You have the row space, but you don't have row null space because they are empty. Means x1 you cannot solve. You cannot have any row that are orthogonal to these three rows. So in your homework, you have to be careful in your homework. In your homework, you have to check. I give you homework, which is matrix is all 4 by 4, 3 by 4 by 3, right? Something like that. I will discuss that later. So sometimes you have a null space, sometimes you don't. It depends on your columns and also your row, and that's the we define the null space and column space. Okay, now here is the fundamental subspace is how you solve it. Of course, now you cannot solve all the space by your hand. So here I introduce single variety decompositions. The single variety decomposition is the method. It's not only one method. There are many different methods to do it, but this is the most stable methods used commonly in solving the subspaces of a matrix. For example, if there's an A matrix, we can decompose this A matrix to be 3 matrices. It's very similar to eigenvalue problem, but it's not. Because if A is a real, all 3 matrices are all real. They won't have any complex. And this, I'll give you an example soon. And this A matrix we can decompose into 3 different matrices, and that's U matrix and sigma matrix and also V matrix. The U matrix can also be decomposed into 2 matrices, one called U1, one called U0. I will explain that to you, what we mean U1 and what we mean U0. And then I have a sigma matrix. This is a sigma matrix. This sigma here is a square matrix, R called R by R, and this it's 0, 0, 0 here, also a matrix is 2, and they are 0 matrix. And we have a V matrix, we also decompose to become V1 and V0, and then parenthesis transpose. Okay. They have very good properties. The single variety decompositions, although this decomposition invented probably more than 100 years ago, however, now it became very practical until mid 60s to 70s, because in that time there were some professors they developed a computational method to decompose a matrix through a computer, and from that on, it has been used in very different disciplines, like in control theory. There are many control methods use single variety decompositions. All right. Now, what do we have here? The E1 transpose and E1 will be identity. All right, carefully, listen carefully. When you decompose this matrix, you can use in MATLAB called SVD, in Scilab also called SVD, to decompose the matrix. And then you will find out after they can decompose it, the E1 and E1 transpose to E1 equal to identity. U0 transpose times U0 is also identity. All right. I will explain that later by example. But now here I just introduce some of their good properties. And U1 transpose times U0 equal to 0. They are so U1 transpose times U0 equal to 0. That means all the columns in U1 are orthogonal to all the column in U0. Alright? What means orthogonal means all the column, every single column times the and all the other column U0, their orthogonal means for any space created by U1, by columns of U1, are orthogonal to all the spaces created by the column of U0. Alright? Don't you think that's a good idea? Good? So if you have a space, column space created by U1, then I have a newest column space created by U0. Right? Does that make sense? The same thing, V1 transpose times V1 equal to identity in the identity matrix. Now I will explain to you that later too. And the same thing, V0 transpose by V0 equal to identity. What does that mean? I explain to you later. And another important sense here is V1, the columns of V1, all orthogonal to column of V0. Alright. Then you will be able to see that later from here, then you will be able to see A1, A equal to U1 sigma V1. So U0 and V0 do not play any role in A. So in other words, U0 and V0 really they don't have anything to do with A. Because what? Because U0 and V0 they are orthogonal to A. They are in other space, not A space. Alright? The A, I already showed you, any matrix you can have the column space. That matrix also have a row space, right? And those two spaces, the column space created by E1, the row space created by V1 transpose. Like that. Just for example. And the other null space of A created by either U0 or V0. Depends on if you are looking at a columns null space or row null space. So here, there's in summary here, column space of A, the basis vectors is U1. Why don't I can use also all the column of A to be my basis vectors. Also, I can use the U1 as my basis vectors because U1 created a color space is identical to all the columns of A creating this color space. You understand? Right? Okay, let me just explain this a little bit and I will write something on the whiteboard. Then the column null space here, the basis vectors of U0 will create a column null space for you. If the column null space is empty, U0 will be empty, won't have any U0 at all. Well, again, I will show you an example and then I come back to talk about this. The same thing with row space. The basis vector of row space can use a V1 transpose. So V1 transpose will create a row space of A, and that is the same thing, that's the same space created by the row of A. The row null space created by V zeta transpose. And then in addition to this, the single values, the non-zero single values, we have sigma including all the non-zero single values, and that single values, the number of single values is the rank of the matrix A. For example, here I have a total of R single values. The rank of my matrix A is R. All right. Any questions? I think it's easy just to give an example, right? Let's look at example. Here, the same example I'm using. And then you will understand what's going on. All right. The single value decomposition of A will create 1, 0, 0, 1, 2, 0, that's a matrix. Then I will get the U, sigma, and V. And U, that's, if you look at this U here, the U here, then I have 3 columns and 3 rows. And those 3 columns and 3 rows, the first two column is my U1. My last column is my U0 and Y. All right, and I explain to you why. Now, the single value here, I have square root of 5, 0 and 0, 1. So I have 2 single values. One is square root of 5. One is 1. That's my 2 single values. All right. So that's the sigma here is the sigma here. The sigma here is square root of 5, 0, 0, 1. That's my single values. My sigma. All right. So for this example, there's nothing here. So this 0, 0, it doesn't appear there. And then I have the last one here is 0, 0. So sigma 0, this 0, 0 column is disappear. There's no this sigma 0, 0, 0, 0, this column is gone. All right, for this case, it's not necessarily always like that. But for this case, it's like that. So I have 0, 0 here. My V matrix now, I have V1 is minus 1, 0, 0, 1. I don't have V0. For this case, I don't have V0. All right? That means my V0 doesn't exist. Just for this case. Okay, so my basis vector for column space will be minus 1 over 5, 0, minus square root 4, 5. That's first 2 columns of U. That's my U1 and 0, 1, 0. So I have 2 columns here. These 2 columns create the same column space as the 1, 0, 2 and 0, 1, 0. All right. Now, the property of this U1 here is the first column is orthogonal to the second column. And also, one more sense. Their length equal to 1. For example, 1 over square root 5, 0, and square root 4 over 5. Take this 1 over square root 5 square is 5, 1, and take this minus 4 square root of 4 over 5, that's 5, 4, add together is 5, 5 equal 1. The length equal 1. So the basis vectors created by SVD, by single value decompositions, the length is always equal to 1, each columns. The basis vector for the column null space will be this, minus square root of 4 or 5, 0, and 1 over square root of 5. And the length of this basis vector for column null space is also equal to 1. And this column null space, the vectors are orthogonal to these two vectors, the E1 vectors. That means they multiply that two vectors, each one is equal to 0. The basis vectors for row space, that means minus 1, 0, 0. And this row space, this row basis vector, I have only 2 rows now. Basis vector only 2 rows. A has 3 rows. But these 2 rows create a space is the same space as the 3 rows of A created. And basis vector for the null row space is empty. That's a V0 transpose equal empty. We call empty matrix. There's no such. So in this matrix, there's no row space. Okay, and then any questions for this example? Do you have any question of this example? Do you want me to explain any more? Questions? You don't understand yet? Okay. Read carefully here, all right? Okay. But this A, I can decompose is the 3 matrix. Now, do you understand that 3 matrix? Okay. You understand that 3 matrix. Then which part of the matrix you don't understand? Tell me, which one? You don't understand.
Basis vector for space.
The vector for space. All right. You mean that's those the basis vector for column space, for example?
No. Basis vector for row space.
Or this basis vector for row space? You mean this one?
Yeah.
Okay. This is just very simple example. It's not always like that. Let me write down something for you. Okay. Let me switch this back here. All right. Let me write down here. I have a 3 row, 1, 0, 0, 1, and 2, 0. Then we know that we can create a row space by we call, okay, now I can create a A1 times 1, 0 plus A2 times 0, 1 plus A3 2, 0. Then I create a row space for any arbitrary A1, A2, A3, right? Agree? Now, for a row space like that, I say I can create a row space. This row space, by the basis vector, I call B1. That's minus 1, 0, plus B2, then the 0, 1. Then I claim this 2 is the same row space. This I create A1, A2, I have 3 three constant here. Here I have only two constants, B1, B2. And I just show you that these two spaces are the same space. Why? Because this 2, 0 and 1, 0, they're the same thing. Right? I can add these two together. This and that. As a matter of fact, that's the same. 1, 0 and 2, 0. So A1 plus 2A3 are the same thing. In other words, these three rows are not independent. They are not independent. However, this minus 1, 0 and 0, 1, they are independent. This, in matter of fact, minus 1, 0 and 0, 1, they are orthogonal. Orthogonal means 0, 1, 0 times 0, 1 equal to 0. Right? So they are independent. This minus 1 times 0, 0 times 1. That means this is orthogonal. So all the basis vectors created by SVD, they are all orthogonal. And they are all independent. You cannot find any basis vectors computed by SVD are dependent. They are not. So this is the row space. Now know that the null row space are empty, means we cannot find any basis vectors to create a null row space. Okay. The current space is the same thing. The current space here, now you create by that two columns. Also the same thing you create by the two columns for this case. And if you look at the basis vector for column null space, then you find out that the basis vector for null column space are orthogonal to the basis vector for the column space. That means U0 transpose times U1, they are all 0. You understand this example now? Any more questions? Good to ask questions. Because if you ask, then I know maybe I can enhance my notes to make it better. The same thing is why I created eigenvalue and eigenvectors, for you to understand that eigenvalues, the relationship between the eigenvalues and natural frequencies and Debye ratio, right? Yeah. Okay. So are we in peace for this example now? Okay, go ahead.
About the vector for column space.
Okay, good.
How to choose the value?
How to choose the value of, okay. All right. That's good questions. For this case now here, we have the sigma, we have two, the important sense is the sigma. The sigma for this case, we're supposed to be like that, but we don't, right? For our case, we have sigma, we have this case, right? So for our case, we don't have this, we don't have that. All right? So now our sigma here is 2 by 2. So we have the square root 5 0, 0, 1, 0, 0. So in matter of fact, this 0 is 2, is 1 by 2. This 0 matrix is 1 by 2. That means this 0 vector. Okay? This matrix is 2 by 2. This 2 by 2. 이거 제거지네. 이거. Yeah. And this sigma here is this sigma there. Alright? So for any diagonal, 0, 0. Alright. Now we have 2, 0 here. Look at this 2, 0 here. 2, 0 important because if you look at the column here, we have 3 columns. U has 3 columns. 0, and then square root 4 over 5. Then I have 0, 1, 0. I have minus square root 4 over 5. Then I have 0, 1 over 5. Right? Can you see it now there? And make sure they see it here. May seem a bummer here. Okay? Maybe you see that side. Okay, and then if you look at this, because I have 2 by 2 here, and 0, 0, 0, and that's, if I have a 2 column here, it means I choose U or 2 column. Alright? If I have 2 column here, then it's 2 column there. And the last column will be this. Why? Because this matrix times that matrix 2 by 2, 1 by 2. If you look at carefully, this times is 0. That times 0, and that times 0. So this column always times 0. That means the last column of this is useless for the matrix A. That means they are in the null space of A. They are outside the A space. That's why you multiply 0. You have 2 0 there. Okay? And then I have the V matrix, this transpose. Now the problem is now I have the V matrix. The V matrix is minus 1, 0, 0, 1 here because the same thing. If I have a 2 row here, then because it's transpose, and if you make a transpose, you have only 2 rows there. I have a 2 column here, right? 2 column. So I have 2 column there, right? Okay? In matter of fact, you don't look at transpose, you look at U. You have 2 column here, you're supposed to have only 2 column there. But because A matrix, the A is 3 by 2. If A is 3 by 2, then U is always 3 by 3. Then this is always 3 by 2, and this will be 2 by 2. And so that one put together 3 by 3 multiplied by 3 by 2 is 3 by 2, 3 by 2, 3 by 2 multiplied by 2 by 2 is 3 by 2. So that's 3 by 2. 这太看不到了哈。Yeah. Okay. Okay. Sorry, I need to write higher. Any questions? That's good. I think the example is easier to explain than the last slides, right? And you are in your homework. Watch out, your homework. Your homework. One example will be something like this. Another example is different. They will have both U0 and V0. Let me just explain to you again. Any questions? Any questions? No? Let you copy here first before I go and move further. Because let us look at example first, and then I give you the, then we can continue. So sometimes you have empty null space, but you always got for any matrix you always got column space. You also got column null space. But I need to explain to you that the basis vector for row space for this case, you can also use the A3 different row as your basis vector. There's nothing wrong with that. All right. But when you use SVD, then they always give you the only independent basis vectors. They don't give you a dependent basis vectors. For A, I have 1, 0, 0, 1, 2, 0. They are not all independent, right? Matter of fact, you look at there, it's easier, right? Then look at this whiteboard. You can also read from here, right? All right. Any further questions before I move to the next page? No? Okay. That's good to ask questions. And let's see. This following 2 pages, I'm not going to talk about that. I'm going to focus on this, just the SVD, right? And the next 2 pages, you will be able, I think you can read by yourself, and that's something which is because I run out of time now. Let's take 10 minutes off. Yeah, 怎么样？可以吧？